For our last section of Chapter 11 about motion, we're going to be talking about acceleration. Acceleration is defined as the rate at which velocity changes. Now remember that velocity is a vector, meaning it describes both the speed and the direction of an object. Therefore, if an object's accelerating, meaning its velocity is changing, that could mean that either its speed is changing, its direction or changing, or both. So acceleration is also a vector. The units for acceleration are meters per second squared. When we talk about changes in speed, acceleration refers to objects that are both speeding up or slowing down. Sometimes you hear the word deceleration. In this class, that also refers to acceleration. It's just going to be a negative acceleration, which we'll talk about later in this section. Free fall is another example of objects that are accelerating towards the ground. Free fall is the movement of an object towards the earth solely because of gravity. In this class, we are going to forget about air resistance and just think about the force of gravity pulling the object towards the ground. If you notice the ball in this picture, every second that the ball is falling, it falls a little bit further each second. So imagine we were taking a picture of this ball as it was falling, and I clicked the camera every second. You can see for the first second, the ball didn't fall very far, but the next second it fell further, and this gap gets bigger each second. That's because the object is speeding up as it moves towards the ground. Objects falling near Earth's surface accelerate downward at 9.8 meters per second squared. So that means that every second, the object's speed increases by 9.8 meters per second squared. So if at this point right here it was at 0 meters per second, the next second it would be at 9.8 meters per second, then 19.6 meters per second, and so on and so forth, gaining speed every second. Now we said that velocity is a vector, meaning that it has both speed and direction. So if you imagine a carousel that's moving around at a constant speed, you may think that the horses are not accelerating because they're moving at a constant speed, but the horses are always changing direction. Therefore, the horses are actually accelerating because their direction is changing. A constant acceleration refers to a steady change in the velocity. The velocity of an object moving in a straight line changes at a constant rate. So just like we were talking about with objects in free fall, the velocity is going to increase the same amount every second. When we calculate acceleration, you're going to divide the change in velocity divided by the total time. Whenever we refer to the change in something, we're going to talk about the final minus the initial. So that means how fast was it moving initially and how fast was it moving finally, and we're going to subtract those two from one another. Be very careful that you're always doing the final speed minus the initial speed when you do your acceleration equation. For this reason, whenever an object is speeding up, you're going to have a positive acceleration. So for example, if an object started with a speed of 1 meter per second and ended with a speed of 5 meters per second, 5 minus 1 is a positive number. However, if we were to switch these two and say the object started with a speed of 5 meters per second and ended with a speed of 1 meter per second, 1 minus 5 would give us a negative number. So negative acceleration refers to objects that are slowing down. So if we were to rearrange these equations to solve for the different variables that we have, this is how it would look. So our first one, acceleration equals final velocity minus initial velocity divided by time. So now let's solve for final velocity. I'm going to circle this equation so we know that it's one that we use often, or put a box around it. Okay. Now, to move the time out of the denominator, I'm going to multiply it to the other side. So I get acceleration times time equals v final minus v initial. Now I'm just going to add v initial to the other side to get my final equation that final velocity equals initial velocity plus acceleration times time. So this is another equation. If we were to solve for final velocity, this is the equation that we would use. And finally, if I wanted to solve now for the initial velocity or the time, so v final minus acceleration times time equals v initial. So this is another equation that we can use. And last but not least, if we were to look at this equation one more time, I'm going to now divide by t to get, divide by acceleration to get time all by itself. So I would end up with my last equation that time equals final velocity minus initial velocity divided by the acceleration. So please write down these equations, and just like we did in the past, we're going to be deciding which equation do we need to use based on our givens and our unknown. So let's do some examples together. A car accelerates from rest to a speed of 20 meters per second over a 5-second time period. What is the car's average acceleration? So this time we're going to have 3 givens rather than just 2. So the car starts from rest. That means that its initial velocity is 0 meters per second. It speeds up to a speed of 20 meters per second, so its final speed is 20 meters per second. And it does this over a 5-second time period, so my time is 5 seconds. So I want to know what is the car's acceleration. A is my unknown, and I use my A equals equation. A equals V final minus V initial divided by time. So now I solve. A equals, always making sure I'm doing final minus initial velocity. That's why it's important that you label which one's final and which one's initial. 20 meters per second minus 0 meters per second divided by 5 seconds. So I get 20 minus 0 is 20, and 20 divided by 5 gives us an acceleration of 4 meters per second squared. Let's try another one. How long does it take a bike that has an average acceleration of 8 meters per second squared to accelerate from 5 to 14 meters per second? So right now it says an acceleration of 8 meters per second squared. So A equals 8 meters per second squared. Now it goes from 5 meters per second to 14 meters per second. These are velocities, and I can tell by the units if I wasn't sure. V initial equals 5 meters per second. V final equals 14 meters per second. So that's its starting speed is V initial, and its ending speed is V final. And I want to know how long will it take. So time is my unknown. Looking at the equations that you've written down, I use the equation time equals V final minus V initial divided by the acceleration. And now I solve. T equals, V final is 14 meters per second minus 5 meters per second divided by 8 meters per second squared. So now I solve. 14 minus 5 is 9 divided by 8 meters per second squared, and I get 1.1 seconds. You can just round it to the tenths place is fine. One final example we'll do together. A sprinter starts from rest and accelerates at 2 meters per second squared for 6 seconds. What is the final velocity of the sprinter? So that should say squared there. So the acceleration is 2 meters per second squared. The other number that I see here is 6-second time period. So I know T equals 6 seconds. Now you might think that you don't see any other numbers in this problem, but when I see the words from rest, right away that tells me that the initial velocity is 0 meters per second. So I want to know what is the final velocity of the sprinter. So V final is my unknown. So V final equals V initial plus AT. It's from my list of equations. And I solve. So V final equals 0 meters per second plus 2 meters per second squared times 6 seconds is 12 meters per second. So this is an example of the types of things that we could be solving for using our given, unknown, equation, and solution. Make sure that you always have 3 givens for these types of problems. Make sure you're also always identifying what the variable is and not just the number. So just like we said with our position versus time graphs, that the slope of a position time graph will give us velocity, if we were to take the slope of a velocity time graph, that will give us the acceleration. So this constant slope from a straight line will represent a constant acceleration. You notice the difference between a linear graph, which creates a line, and a nonlinear graph, which is a curve. A linear graph is one in which the displayed parts the displayed data form straight line parts. So just like the word line is right there in linear, it makes a straight line. So these 3 graphs are all velocity versus time graphs. Graph A, you can see that the velocity is increasing. So this would be an object that is speeding up. The velocity is also positive, you see, because it's above the x-axis, so this object's moving to the right. Now in graph B, you may think that it's slowing down because it has a negative slope, but this one is also speeding up. If you think about the fact that 0 velocity is right here at the x-axis and it's moving in the negative direction, it's speeding up, but it's just going in the negative direction. For this object, you'll notice that the slope is 0. That means that this object is moving at a constant speed. This speed is also positive the entire time, so it's moving at a constant speed to the right. Now this one here, now that this is in the negative end of the y-axis, this one is also moving at a constant speed, but it's moving to the left. And also keep in mind that these are all velocity versus time graphs. For distance time graphs, how would it look if we were having an accelerated object? Accelerated motion is represented by a curved line on a distance time graph. We call these nonlinear graphs, where a curve connects the data points that are plotted. The slope of a curve increases as the speed increases. So looking at these graphs, if I were to look at how does the slope change over time, that will tell me how the speed of the object is changing. So for this object, it starts very steep, a very steep slope, and then it gets flatter and flatter. That means the object is slowing down. However, this object, the slope starts very flat, and then it gets steeper and steeper as time goes on. That means the object is speeding up. So always pay attention to the slope, and keep in mind, the slope of a distance time graph gives you the velocity, and the slope of a velocity time graph gives you the acceleration. And just like we talked about the difference between average velocity and average acceleration, the same is true for instantaneous acceleration. Instantaneous acceleration is how fast is the velocity changing at a specific instant. The length of the vector depends on how fast the velocity is changing. So we can map out accelerations just like we can map out velocities and displacements or any other vector quantity.